Hello, my name is Alex Ruane, and I am from the NASA Goddard Institute for Space Studies in New York City. I am going to be talking today about how NASA uses Earth information in support of agricultural modeling applications. The agricultural sector of the future may not look like it does today. The world is asking the agricultural sector to take on a quadruple challenge in the coming decades. There is pressure to sustainably increase production to provide healthy food for growing and developing populations, to adapt to climate change and ongoing climate extremes that we already see all over the world, to mitigate emissions, recognizing carbon exchanges and other greenhouse gases from agricultural lands, as well as opportunities therein. And of course, all of this must be done in a way that maintains financial incentives so that agricultural production moves forward. NASA scientists are leading global efforts to apply agricultural models for a wide variety of decision support systems. Scientists at NASA GISS are coordinating the Agricultural Model Intercomparison and Improvement Project, or AGMIP, which is an international network of more than 1,000 crop, climate, livestock, economics, and health systems experts that are working to understand how we can use agricultural models to extend beyond our observed experience for applications related to things like the identification and prioritization of alternative agricultural strategies. For example, what would the world look like, or what would a given farm system look like if there were different sources of irrigation, or if there was a different management strategy or planting date? Or likewise, we can extend this into the full food system to explore different value chains, for example. This allows us to connect our models to assess complex food systems, not just looking at biophysical crop production models, but extending into economics and health. We also can look at different ways to sustainably and profitably manage land, water, and energy resources, and can use these models with our stakeholders, with our partners, to build resilience today and prepare for future challenges. The figure on the left shows an important perspective on corn production all around the world. Corn is grown in many, many portions of the world. Pretty much anywhere there is arable land, you'll find some kind of corn. And you'll notice that many parts of the world, here represented in blue, have small amounts of production, but some areas are concentrated with the highest production, as you see here in greens, yellows, and reds. This is the global corn production, but in many cases what markets and producers and commodity traders see is something more like this, which is the centralized portions of the world that you need to produce 90% of world corn production. These areas are breadbaskets of the world and are incredibly important in terms of overall global production and food security and many aspects of our food systems. You'll notice that the heaviest concentration of corn production is in the upper Midwest, but of course there's also production in portions of South America, Central and Eastern Europe, North China, and sporadic production in some other places. It is important that we understand these different perspectives on corn production so that we can serve different farmers' needs and understand, for example, that droughts in the US Midwest have an outsized impact on the world. This allows us to look at corn production and other agricultural commodities in terms of where the climate impacts and other droughts and floods and extreme heat may have the largest impact on human lives. Our agricultural models allow us to look at fields from a variety of perspectives. Of course, they're not the only thing we can use to look at fields. We utilize all available tools. We looked at direct observations in terms of surveys and reports, working with colleagues at USDA and other places. Of course, we also have remote sensing of weather information, as well as the vegetation itself and the soil status within fields. But crop models give us an additional perspective because they allow us to capture specific biophysical processes and responses to genotype, environment, and farm management. They also are able to look at interactions between complex systems so that we can see compound events and other unobserved interactions. For example, this is a system diagram showing that a crop model is able to look at interactions, for example, from irrigation, fertilizers, greenhouse gas and other gas exchanges, weeds, pests, diseases, farm management, air pollution, mechanical equipment, and of course interactions throughout the soil level. This is an important way that we can understand not just what is happening from space, but also understand what all of these observations mean when we put them together into their biophysical context. Advances in high-performance computational systems now allow us to run crop models at high resolution, even across very broad domains. This is an animation of runs that we have over Iowa with corn in shades of yellow and soy in shades of green. And you'll see that we have very high resolution, but that there are still some stark lines, which are because of our data limitations that sometimes on a county level tell us about cultivar selection or management choices. We look at these across the years so that we can identify bad years, like the 2012 drought showing up now, and understand why these impacts are happening and what they mean on a field level. At high resolution, of course, you can see that there are crop rotations, and there is information even at a subfield level that helps us understand different impacts and also connect our high resolution remote sensing information into specific biophysical processes within and across fields. Another thing we look at, of course, is the aggregation of all of these fields and what they mean when global production is traded through various value chains and international markets. This is a systems representation of the way that that commodities come off of fields and come out of past the farm gate into a longer value chain of processing and transportation, maybe interacting with customs and tariffs, interacting with international markets through imports and exports, but also being an integral part of food aid, and also a market that is potentially vulnerable to shock events that can loop back into all of these systems, affecting even local markets and consumers. This is one of the reasons that we are interested in extending our information from the fields into their global context through food systems. Understanding complex food systems requires us to span different scales and different types of modeling. We therefore look to provide agricultural information that connects biophysical information with economic information, as well as regional information with global information. One way to think about the connections here is by following this diagram, starting in the upper left, understanding that what happens on a typical farm household that might include some variety of cereal crops, vegetables, livestock, and decisions made within the household, what happens on those farms combines to cause different levels of global crop production in the upper right. The sum of that global crop production feeds global markets and sets prices through trade. And then what happens across that global market in turn affects regional markets and prices, which connects back to our upper left portion of the circle here, because what happens next year on the farm is going to be influenced by those prices. This whole circle connects across these disciplines and across these scales, and is in turn affected by things like climate, development, changes in policy, and dietary and other nutrition scenarios that we can use to explore models in each one of these circles and their connections across this whole complex system. When we are using our agricultural models, we usually start by understanding what is happening today. Our crop models need to respond to hazards and disasters, for example, cyclones and extreme storms, pests and diseases, air pollution, but even more fundamental processes like temperature extremes ranging from the cold to the hot side, as well as rainfall extremes, including both drought and flood events. This perspective on what's happening today allows us to have real-time and seasonal outlooks that range from monitoring up to the present day and forecasting out into the seasonal future that is to come. We can also look backwards into the historical period using these same types of agricultural models to understand what has happened to cause good or bad years in the past. We can detect and attribute the causes of those changes, and we can even explore counterfactual management. For example, could we have done better in the 2012 drought had we planted at a different date or used a different corn variety? This gives us understanding and allows us to understand retrospectively what has happened. Beyond the end of the season, we start to see big effects of long-term trends, things like climate change, changing market influences, shifts in policy, socioeconomic development, and large-scale environmental sustainability shape these long-term outlooks. At this point, we can no longer predict what will happen, but we can project what would be the outcome of different types of trends that we are currently setting right now with our current actions. Across all of these timescales, across all of these types of hazards and disasters and approaches that we're taking, it allows us to understand the past, create reactive interventions for the present, and be proactive so that we can be prepared for the future to come. One glimpse of the future is provided by recent projections on climate change impacts across the world. These animations that you see here are maize or corn yield projections and wheat yield projections progressing out into the end of the 21st century from an ensemble of crop models provided through AgMIP using different climate model projections. And in this case, we are holding the current management constant. So this is just the effect of climate without any reactions. But what you see here is increasing pressure because of the climate system on yields that will force some kind of response over the long term. You can notice right away in the bottom left that maize or corn yields are declining in most parts of the world and reaching very high levels of decline. Whereas wheat yield has some places that are going up and some places that are level and others that are declining. This is owing largely to the fact that maize is a C4 crop and has a weaker response to carbon dioxide, whereas wheat is a C3 crop with a stronger response. But even for wheat, you'll notice that there are very important bread baskets that are reducing in yield. For example, most of Mexico, northern India and Pakistan, and portions of South America see wheat yield declines, even portions of southern Canada and the upper Dakotas. This is a challenge that is going to be increasingly apparent, and NASA is eager to work with farmers and agricultural system managers to prepare for these challenges so that we can use agricultural innovation to be resilient and take advantage of any opportunities that may come. Our analysis of future climate impacts allows us to look at specific hazards, for example, new hazards that are affecting agricultural seasons in the future. What you see here in shades of orange are places that currently do not have extreme heat in the middle of the growing season, but in the future they will. In light orange by 2050 and in dark orange by 2100. You can see that extreme heat becomes a new hazard for many portions of the northern United States and southern Canada and moves up into the mountains in portions of the western country. In contrast, places that are removing hazards, for example, no longer face a frost hazard by 2050 or by 2100, are shown in shades of blue. But you might notice that the places that remove the frost hazard are many fewer than the places that have new heat threats by the end of the century. Projections of the future also show us that conditions will be increasingly dangerous for agricultural laborers. Here is a analysis of future climate projections where we are looking at the NOAA heat index, which is a combination of extreme heat and high humidity that affects people's ability to perspire and regulate their own heat. What we are showing here is the number of days per year where the heat index exceeds a threshold of 103 degrees Fahrenheit, which is NOAA's danger level. This would be any day of the year where this condition occurred even once. In the bottom left, you have a moderate emission scenario, and in the upper right, you have a high emission scenario. And this is the ensemble of more than 20 climate model projections. What you see is that there is an increasing number of extreme dangerous heat days in each year. And especially this is notable in portions of Africa, but even in parts of the US in the bottom right, you can see these lines drawing forward, showing how portions of Florida and Texas and California and the upper Midwest are increasingly exposed to these types of extreme heat days. These will require different approaches in terms of how field laborers manage their fields, different times of day perhaps to work in the fields, but also an increasing challenge for laborers' health conditions. In conclusion, NASA is happy to be at the Commodity Classic because we want to work with you. NASA connects an incredible array of observational tools with agricultural models so that we can apply them to address future food system challenges. Local, regional, and global planning benefits from our ability to explore unobserved systems and interventions in our models. and allows us to virtually test many new strategies so that we can identify and prioritize specific field testing and implementation programs. We can use these agricultural models to understand complex dynamics of unintended consequences and feedback loops so that we can be most efficient with what we bring to the fields. I'm happy to speak with anybody about further explorations and the way we can use agricultural models and NASA tools to support your activities. And my contact information is here, as well as a link to AgMIP's website. Thank you so much.